Sugam Prabha. Digital India. Educated India.
Hello students, in this lecture clip I will discuss wave equation again, but this time for semi-infinite string. Okay, in the previous lecture I discussed wave equation for infinite string and I show how to obtain dilemma solution. Today we will see that how this solution has to be modified if the domain is half line instead of full line. So let us start. So let me write down the problem first. This is wave equation for semi-infinite string. Okay. So first let me write down wave equation. Del square psi del t square equal to c square del square psi del x square, where here x belongs to 0 infinity and t greater or equal to c. Let us label it as 1a. Okay. As usual, as before, there will be initial condition. So psi x0 equal to fx, psi t x0 equal to gx, x belongs to 0 infinity. Let us label it as 1b, and there will be boundary condition. For previous case, which I discussed in the previous lecture clip, there was no boundary condition because the string was free from both ends, sufficiently long string free from both ends. So we were propagating both towards left and towards right direction, right? This time, a sufficiently long string is one end is tight at x is equal to 0. Other end is free. So we will be propagated in the one direction only, the direction where string is free. So at x is equal to 0, we need a boundary condition. So let us take boundary condition is okay, t greater or equal to c. Okay, now what is the difference here? You see, as before, as in the case for infinite string, we may proceed by reducing canonically, okay, and get a solution which is psi xt equal to phi 1 x plus ct plus phi 2 x minus ct. Let us label it as 2a, where phi 1, phi 2, I am writing on the next page. Phi 1 x plus ct, okay, phi 1 x plus ct, it was half f x plus ct, right, plus 1 by c integral x0 is some arbitrary point 2x plus ct GUD. Let us label it as 2b, and phi 2 x minus ct, this was half f x minus ct, okay, minus 1 by c x0 to x minus ct GUD. Let us label it as 2c. Now, for this problem, what is the difference? Because so far, solution to what I have written here, it is in the same procedure what we did for infinite string. Point is that here, that functions f and g, note that f and g are defined only for positive argument. But x minus ct less 0 for x less ct. This means equation 2b is perfect for x belongs to 0 infinity and t greater or equal to 0. But equation 2c is meaningful only for x belongs to ct to infinity, t greater or equal to 0. Understand? Because these things, when the argument x minus ct will go to negative, f is not defined there. So equation 2c has no meaning. So what is the takeaway then? I am writing the next page. Thus, we need to find correct phi 2. Let's say any dummy argument phi 2v for v less g. How we can do that? Boundary condition. Okay. So boundary condition is, let me see what is the boundary condition. Boundary condition is psi 0t is 0, right? So use boundary condition, which is psi 0t equal to 0. So that means psi is phi 1 x plus ct. I am putting x0. So phi 1 ct plus phi 2 x minus ct. I am putting x is equal to 0. So phi 2 minus ct must be equal to 0. What does it mean? Hence, we understand that phi 2v equal to minus phi 1 minus v for v less 0. So we got a relation between phi 1 and phi 2 for negative argument. So therefore, for x is defined from 0 to infinity. So for 0 less or equal to x less ct, phi 2 x minus ct, it is less 0 now. It should be minus phi 1 ct minus x. And then let's go back to show you what is phi 1. It is phi 1. So we will replace now argument x plus ct by ct minus x. So it should be minus half f ct minus x. Okay. Plus 1 by c x0 to ct minus x GUD. So there was equation number 2c. So let's say it is 3. So now we correct phi 2. We got correct expression for phi 2 for x less ct. So for x less ct, we can write down the solution. Therefore, for 0 less or equal to x less ct, psi xt, it will be phi 1 x plus ct plus phi 2 x minus ct. Now phi 1 x plus ct is half f x plus ct plus 1 by c x0 to x plus ct gu du minus half f ct minus x plus 1 by c x0 to ct minus x gu du. Okay. So now we can group these two integral x0 to x plus ct, and this minus can be absorbed here to take ct minus x to x0, so that x0 will disappear as before. So your solution will be for 0 less x less ct, psi xt equal to half f x plus ct, okay, minus half if ct, sorry, half not required, I will take half outside. So minus f ct minus x and plus 1 by 2c ct minus x to ct plus x GUD. This complete solution, because in next page I am writing down the full solution in the full line, in the half line where the problem is defined. So thus solution for semi-infinite string, we can write in this way: psi xt equal to, for x greater ct, the solution is same as was the solution for infinite string. Okay, so it is half f x plus ct plus f x minus ct plus 1 by 2c integral x minus ct to x plus ct gu du. This is for ct less or equal to x less infinity. And for 0 to ct, that's just what we obtained in the previous page, half f x plus ct, okay, minus f ct minus x plus 1 by 2c integral ct minus x to ct plus x gu du, 0 less or equal to x less ct. Okay. One final comment. This completes the discussion how to obtain solution for semi-infinite string. One final comment is, if you look into the expression of solution, the solution is, however, continuous at the point x is equal to ct. So you can put in both places ct. Okay. Now, I have to discuss third case of wave equation, which is finite string. But before that, I want to introduce Fourier series. I will not go into detailed discussion, theoretical discussion of Fourier series. that you can find in any analysis book. I will write down the standard results so that it can be used by you to find Fourier series solution of wave equation for finite string, or even in heat equation and in Laplace equation, you need the conception of Fourier series. In fact, perhaps in 1807, celebrated mathematician Joseph Fourier invented this Fourier series in connection with the study of heat flow over a metal body. Okay, because that time, without Fourier series, it was not possible to express the Fourier series, express the solution of this heat problem compactly. Okay, so this is the source of inventing Fourier series. Okay, so I will just write down the standard results of Fourier series, and also I will write down one generalized Fourier series. Okay, so we can start in this way, that suppose fx is periodic, okay, or periodic function, let's say, of period two pi defined on real line. Then we can expand. Fourier series means it is expansion in terms of sine or cosine functions. Okay, these are expansion. So then we can expand fx as an infinite series of sine and cos function in this way: a0 by 2 plus summation n equal to 1 to infinity an cos nx plus bn sin nx. Okay. Now you see, I am not discussing all the constants imposed on fx. Of course, there is some constant like fx must be piecewise continuous, at least, to write down in this way. And also this infinite series will be assumed to be, in that case, term by term integrable or differentiable. Okay. We are not interested about theoretical discussion. We are interested about the results. Results means, okay, we have to know that fx can be written down in this way. So let me label it as a.1. This is Fourier series. So we may write a title that Introduction to Fourier series. Okay, so point is that then this an and Bn A0, this can be written down using Fourier inversion formula like that, where An equal to 1 by pi, okay, integral minus pi to pi, okay, fx cos nx dx, and Bn equal to 1 by pi minus pi to pi fx sin nx dx, where n equal to 0, 1, 2, so. Look here, I wrote down two formula for n equal to 0, 1, 2. In normal textbook, you may find Bn only starts from n equal to 1, 2. Actually, the point is that I wrote it compactly. Now you see, if you take n equal to 0, this B0 is of course not here. But this B0 is equal to 0 here, identically, because there is a sine function. So this results we have to remember. Okay. So when you will solving wave equation for finite string or heat equation, Laplace equation, you will obtain a Fourier series. And from that, using this formula A.2, you have to find out the coefficients. Now, some more points you have to know. What is that? I am writing down in the next page. First point is that any 2 pi periodic any 2 pi length, what I want to say, any 2 pi length period can be taken. That means in previous formula A.2, I integrate over minus pi to pi. But one can take, it is based on the problem at hand, you can integrate 0 to 2 pi. That is also valid. Any 2 pi length period from real line can be taken. This is first thing. Second point is that Fourier theorem is much generalized theorem. I start by saying that function is periodic, it is true. But Fourier theorem is applicable for non-periodic function too. Now, little adjustment you have to do. How? Suppose consider these special cases. Suppose fx is defined only on, let's say, minus pi to pi. Okay. So that f is no longer periodic. Right? Then you can make a periodic copies. How? Construct a new function capital Fx, which is equal to Fx for x belongs to minus pi to pi. Okay. And outside this interval, you impose in this way, fx plus 2k pi equal to fx outside minus pi to pi. So what happened here? F is periodic, right, on full real line. So apply Fourier theorem. Apply Fourier theorem on F. Okay. But our interest will be expression of f in minus pi to pi, because it is the interval of interest. To apply Fourier theorem, we make an identical copy of that function profile, which was in minus pi to pi. We, in each such 2 pi length, we make an identical copy both sides to make it a periodic. So we can apply the Fourier results, which I stated at the beginning. This is one case. Another special case is, function may not be defined on 2 pi length interval. Maybe it is half length interval, it may be defined. So this is another case, that suppose fx is defined on 0 pi. Of course, not periodic. But here, another thing is that even length of interval is not pi, not 2 pi. We need 2 pi length, no? Because we are expanding in terms of sine cos, which are periodic function of period 2 pi. In this case, you need first an extension on the left half, minus pi to 0. An extension may be possible in 2 ways: odd periodic extension and even periodic extension. So let me write down. Here we need periodic extension, or maybe extension, not periodic extension, just extension. So periodic will come later. So we need extension of f in minus pi to 0. Two ways possible. One is even extension. Even extension means for x belongs to minus pi to 0, that means f minus x will be equal to fx when x belongs to minus pi to 0. Even extension possible, odd extension possible. Odd extension possible, where you will define f minus x is equal to minus fx, where x belongs to minus pi to 0. So then, as in the case, special case 1, you can now construct a function capital F, okay, which will be fx, extended fx, equal to extended fx on minus pi to pi. And outside this minus pi to pi, in all other 2 pi length intervals, it will be identical copies. So we can apply Fourier theorem. So here one thing you have to remember, that for even in both cases, in this case, you will get a half range Fourier series. That means either cos or sine. The full series, what I wrote at the beginning, it is called full range Fourier series, which contains both of sine term and cos term. Here it will be half range series. For even extension, if you take even extension, okay, then your fx will be a0 by 2 plus summation n equal to 1 to infinity an cos nx, where this for even extension, where n will be the 2 by pi this time, okay, integral 0 to pi fx cos nx dx. And for odd extension, this is called half range Fourier cosine series. Okay. Now for odd extension, you will have fx equal to summation n equal to 1 to infinity bn sin nx, where bn equal to this time 2 by pi integral 0 to pi fx sin nx dx. Okay, this is one special case. So these two special case is fine, but still one more thing need to be pointed. What is that? F may not be 2 pi period always, no? So in general, F may be of period, let's say 2L. It is possible. Only thing what you have to do here, change a scale change, okay? To change the variable x to x prime equal to no, pi x by L. So you actually map the period. So pi x by L, so that you have I am writing the beginning results, which I wrote for 2 pi periodic function. This time I am writing in general 2L periodic function. So fx is equal to a0 by 2 plus summation n equal to 1 to infinity an cos n pi x by L plus bn sin n pi x by L. Okay, where you see watch the argument is changed now, n pi x by L. Okay, so where an equal to 1 by L integral minus L to L fx cos n pi x by L dx and bn equal to 1 by L minus L to L, okay, fx sin n pi x by L dx, where n equal to 0, 1, 2, so. This completes our introduction to Fourier series. No? This will suffice our work. We are actually interested to find solution of wave, heat, and period and Laplace equations. So this up to this is fine, but I want to introduce a generalized Fourier series. There are many generalized Fourier series. I will actually want to give you the result which will be required for 3D Laplace problem. It is called Fourier-Legendre series. Now, I'm not sure that what you are aware or not about Legendre polynomial. It is a very special type polynomial. Its definition, it is denoted by P. I am giving you definition of Legendre polynomial. It is Pn. N means degree of polynomial. Its definition is summation m equal to 0 to capital N minus 1 to the power m 2n minus 2m factorial by 2 to the power n m factorial n minus m factorial n minus 2m factorial x to the power n minus 2m, where capital N equal to n by 2 or n minus 1 by 2 according as small n is even or odd. So by this definition, you can write down some few fast polynomials like P0x. If you put here, you will get 1. P2x, it will be x. Okay, in this way you can write down P1x equal to x. So P2x is half 3x square minus 1, etc. Okay. Now, a function fx can be expanded, okay, in the basis of Legendre polynomial. Like Fourier expansion, there was sine cosine function, here will be Pn function. So I am writing down this expansion. It is fx equal to summation n equal to 0 to infinity an. This an is called Fourier coefficient. This time we will call Fourier Legendre coefficient because it is Fourier Legendre series an Pnx. Okay, the formula for an by inverse theorem, an equal to 2n plus 1 by 2 integral minus 1 to 1. This minus 1 to 1 is the interval where all family of Legendre polynomials are defined. Okay, so minus 1 to 1 fx Pnx dx. Okay, so this completes all about Fourier series. So let me go now to wave equation for finite string. Okay, so write down title wave equation for finite string. So a string of length L is tied at both ends. So this time there will be boundary condition at both ends. So let me write down the problem. So essentially differential equation is same, which is del square psi del t square equal to c square del square psi del x square. X belongs to 0L and t greater or equal to 0. Let us label it as 1A. There will be initial condition as before, which is, let's say, psi x0 equal to fx and psi t x0 equal to gx. Okay, and there will be boundary condition, which is, let's say we are taking psi 0t equal to 0 and psi lt equal to c. Let's say 1c. So if you recall my first lecture, motivational introduction, there I discussed what is method of separation. Okay, so we will use here this method called method of separation. Okay, method of separation to find solution of problem 1. What is method of solution? Here we assume, as we discussed in the introduction, here we assume solution in separable form, like psi xt equal to, let's say, capital X of X, product of capital X and capital T, where capital X is function of X only, capital T is function of T only. Okay. So if you substitute this, solution 2 into 1, as I discussed in the motivational introduction first lecture clip, that you can separate, like you see here, you will get x double prime. Double prime means the ordinary derivative of second order. So you will get x double prime. Double prime means second order ordinary derivative with respect to its argument. Okay, x double prime by capital X equal to t double prime by c square t equal to, let's say, minus k square, because both sides must be, if for equality of both sides must be separately constant. So we are taking this constant. It is minus k square is just for convenience. K square, if you take k square, then in the solution root will not come. But at this moment, you have to understand that this k is not known. Whether it is real or complex, what are its values, okay, we don't know. So, okay, then now you see 2 implies basically equation 2 implies 2 eigenvalue equation, right? One is x double dash equal to minus k square x. Again, I am telling this eigenvalue equation also I discussed in the first clip in the context of differential operator. So these two I told that in the middle of the course or in the advanced stage of the course, it is not possible maybe to discuss this method. So I introduce it in the motivational introduction. So t double dash, this is equal to minus c square k square capital T. Okay. Separately, because we don't know what is the value of k. So in this type of problems, always we separately consider k equal to 0. Whether it is allowed or not, we will see. So consider k equal to 0 case. K equal to 0 will imply capital X will be ax plus b. And if you apply boundary condition, then you will have a equal to b equal to 0. Therefore, k not equal to 0. Why? Because eigenvector cannot be 0. Okay. So, therefore, from now on, we will consider k not equal to 0. But we don't know k is real or not. K may be complex, k may be imaginary, anything may be possible. We have to find out k as well as find out x and t. Okay. That's why it is eigenvalue problem. Okay. So you see, from the solution of it, we can write down as leveling x kx, okay, equal to c. This is arbitrary constant. I am just leveling k here because you know eigenvector will be corresponding to eigenvalue k. C1k cos kx plus C2k sin kx, okay, and tkt will be d1k arbitrary constant cos ckt plus d2k sin ckt. Now, today I will stop because time is up. And I wanted to stop here because I now again want to give you a homework. What is the homework? Use boundary condition, okay, and initial condition to find C1k, C2k, okay, D1k, these are all family. So not a single constant. Why family? For values of k, okay, D1k, D2k. Try to find out. And k itself. This is the eigenvalue. Try to find out. In next class, I will show that how to use BC, IC to find this constant and eventually to find the solution of wave equation for finite state. Okay. So this completes our problem for our class for today. Next class I will again take up. So do your homework. That's what I did at the last line. Maybe interesting.